Okay, Tuesday, lab 10. So once again, I'll repeat it for the recording. I'm thinking about 1.3, 1.5, and problem 2 to show solutions for. And the rest of them I'm going to leave as like skeleton code. Mostly filled out, but I mean, the skeleton code, the parts of it I took out for the skeleton code. That's the part that like wasn't explicitly said in the PDF. I'll give you an example. Like, for example, Taylor convergence, it looks like I filled everything out already except for like one line. But I mean, this stuff's already in like the input description in the PDF. So yeah, there's not much to fill in here. So we'll start the first one. Why not? I'll give a quick outline before I start of what this kind of looks like. I'll need to plug in my drawing pad. There we go. Okay, so part 1 is like all right, problem 1. It's like a 5-parter. There's like 1.1 and 1.2. This is like, it all goes under the umbrella of like my sign. Here's 1.3, 1.4. This is like my sign periodic. My sign period. What this is it's 2 methods of doing the same thing, like finding the sign of a number, some angle. And like the first one's not going to be very good. I'm going to write like not good. This is better. We're going to modify it so it's better. And 1.2 and 1.4 are like, let's check how good these are. How different is this from actual sign of x? And then 1.5 is like, we're going to use like interpolation, interp, to find sign. It's like kind of like, you may have seen those like sine tables that you were like printed out and it said like, oh, 30 degrees, sine of 30 degrees is this number. Sine of 45 degrees is this number. That kind of thing. You may have used that in high school, that kind of thing. Okay, so that's part 1. Well, problem 1. And then problem 2, we're going to do actually in depth. It's like my Lagrange. Basically, that's just, you have a bunch of points, 1, 2, 3, 4. What's the lowest number, what the lowest degree polynomial that passes through all those points? So for this one, it'll be like a cubic. 1, 2, 3, like that. But that's a little bit ahead of where we are. Let's start with, let's go in order. Okay, everyone good so far? Quick question / concern check. I'll clear this annotation. 3, 2, 1. Here's the first part. This is our not so good approximation of sine. I'll leave this as skeleton code. You're going to want to have first of all, let's go over the inputs. You're just given a bunch of x's, like it throws a bunch of x values at you, like I don't know, 5, 2, 3, pi, 2 pi. All those are in a matrix called x. And n is like the number order Taylor expansion. So check the PDF for how to get the nth order Taylor approximation of sine. Like you may have seen this x, it's like sine of x is approximately x minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial, etc., etc. So like this keeps getting bigger. Like this more and more exact, I should say. The more terms you kind of tack onto this. And like the nth order, just this kind of tells you like what position to stop at. Oh, before I forget, let me create breakout rooms. I forgot to do that. Did I do that already?
I already created them.
Oh, sorry. Okay. Thanks.
Let me know in the chat if you have any questions or if you want to get the problem 0 checked off.
So my sign mostly based on PDF. Thanks, Nikolai. Taylor convergence. This is just it's a test of my sign. How close is it to sine? I mean, you can kind of see from the error over here. So absolute value of sine series, which is like the output of my sine, versus regular old sine of x. How different is our result from our given. And this error is going to change depending on how exact our Taylor approximation is. If this ends like 2, then it's not going to be very good. But if it's like 1,000, then of course it's going to be very exact. And then the next term, you'll find something in the PDF about how to get this next term. I think it's like literally in the output, but okay. Sine periodic. This one's like mostly filled out already, but like I want to ask a kind of a conceptual question to everyone. Should this be less than or greater than? Okay. So first of all, let me explain what we're trying to do here. So my sine periodic, the idea is, remember like our bunch of x's, right? I'm going to write like 3 pi, negative 3 pi, pi, negative pi. Let's say that's our x. So normally we wouldn't do anything. We'll just like take this and then stick it in the Taylor approximation. But one thing we can do to make it more exact is whenever we see like a 3 pi, we can change that to like a pi and this to like a negative pi. Why can we do that? Well, we're just taking off 2 pi. Because remember, like the sine function is periodic. Like it has a period of 2 pi. So if we have 3 pi, right? This is 3 pi, but it's also pi. Like if we actually drew this out like a Cartesian graph, like this is pi, and we just circle around if we want to get 3 pi. So we just kind of like undo that circle and we get back to pi. The reason we're doing this is the Taylor approximation is like less exact the further away we get from 0. 3 pi is not going to be as exact as pi. So we're going to try and like cram everything back into the domain of sine. Here's my question to you. The way I've set this up is like I've had this in a while loop where we have, while this thing is further away from 0 than negative pi and pi, like let's say here is the number line, negative pi, here's pi. I'm going to try and bring this back towards the origin, like in increments of 2 pi. Let's say I arrive at negative pi. See something in the chat. Okay. Let's say I'm at negative pi. Do I go another 2 pi? Do I like bounce over here? Or do I keep it at negative pi? This is like check the PDF on this. I want people to kind of take a look at that and see which one of these is true. So I'll give you guys like a minute to look at that. Should this be a less than or less than or equal to? And explain why. The answer to this is like, if we're at negative pi, do we keep going? Do we do we add on another 2 pi, or do we just stay at negative pi? Is it okay to stay at negative pi? Drop a big hint. Is this closed bracket or is this open bracket? And if you're confused, tell me why. And which part?
Open bracket?
Why do you say open bracket?
Because we're not doing less than or equal to, we're doing just less than or greater than, and then we're
my question is
after the while loop.
My question is, do we use less than or less than or equal to? I mean, this is the choice we're making.
Oh, and that's why we're determining whether open or closed bracket.
Yeah. Check the PDF.
Okay, maybe it's closed. Yeah.
In the PDF, it says closed bracket. It says closed brackets.
Gotcha. Closed bracket. So what does that tell us?
Less than or equal to.
Why say less than or equal to? If it's closed bracket, that means negative pi is okay, right?
Oh.
Yeah, that's tricky,
Yeah.
right? You associate with this with like closed bracket, but this is a while loop. Like while we're outside of negative pi, so this is okay. Negative pi is okay, and pi is okay as well. So because of that, this should be what? What should go here?
Just less than.
It should be less than, and this should be greater than. Because if we said less than or equal to or greater than equal to, that means that negative pi and pi are not okay. We're still in this while loop. So we'll need to add on or subtract of 2 pi from that. So that's not what we want, according to the instructions. But if the instructions didn't specify that, we can code it however we want. That's just like 1 point on the number line. So now that we have that, we can do this as normal. Like we just apply my sign because we just modify the x input. We're just like kind of, we're taking x and then we're kind of like squeezing it into negative pi and pi. And then we can just do my sign as usual. Or if we want, we could just like write out the entire like code of my sign in this if we wanted. Or we just call it for simplicity's sake. I see some things in the chat. Okay. People's getting checked off for, if you guys want being checked off for problem 0, talk to Nikolai. He can do this while he can do that while I'm doing this. Okay, clearing in 3, 2, 1. That was my same periodic. That was 1.3, one of the ones I showed full solutions for. And here it's just another error check. How are we going to check whether this thing is accurate? So kind of filled all this a little bit of this already. It's a little bit different than 1.2. Here we're going to use like an anonymous function, non function. And what that's going to do is like it'll allow us to apply this f0 function, which it finds the roots of the function you give it. So f0 of like some function. Let's say like I'll draw like a parabola. Now let's not do a parabola. Let's just do like a cubic. And this is some function that we can graph. And here's like the x and y coordinates. It's going to find where this thing equals 0. That's all that does. And the angle, the physical meaning of that is the angle at which, so what this means is this, where does our sine periodic function be a tolerance difference from sine of x? So like, let's say my sine periodic minus sine of x. And then like this difference is like, I don't know, 5, like they're different by 5, or I don't know, like 5 to the power of 5 times 10 to the negative 10. Let's say that. And then that's our tolerance. Where does this like stop being okay? Like our my sine periodic is going to change, like depending on like our n. So at what point is this going to like stop being okay? Like it's a little bit tough to explain, but all we're doing in this part over here, all we're saying is if it's greater than some angle, if this angle that we find is greater than some quantity, then that means our sine periodic works everywhere. So I can't go into that without like spoiling the answer, but think about that a little bit as you're doing that. I'll go to the next one in 3, 2, 1. Here's the sine lookup. There's a couple ways of doing this, but here's the formatting that we're kind of working with. We'll need to understand this before we do anything. We have the x as usual with a bunch of 2s and 3s and 5s. Pi, 2 pi, 3 pi. And we'll have a table. That's not really a table. It's just a some number by 2 array. This is our table. And what these mean are, here's the angle, I'm going to call it theta, and here's like our sine theta. What angle are we at? And this is in degrees, by the way. So that's an important thing to pay attention to, degrees. And this is the sine at that angle that we're given. 30 degrees, 45 degrees, that kind of thing. And here's where we'll extract from the table. Extract columns. I'll write calls. This you may see as a bit familiar. I mean, it's just the same thing we're doing with like my sine periodic. We're adjusting it so that it's within the domain of sine. Okay, I'll leave this as an exercise, I think, for people to kind of try out how to do it with the mod function. So how to like change this part and this part into just like one single line. But that's on you guys. Make sure that you remember this. X is in radians versus the tables in degrees. So we'll convert from radians to degrees. So we want this to change to like, okay, I'm not going to try and do that calculation. 360 over pi or something, etc., etc. Initialize sign table. Now here's where I know I put this as like a single ellipsis, but this is actually a pretty meaty part of code, piece of code. I'm gonna clear the annotation so we have space in 3, 2, 1. Okay, here, so bear with me. This is what we're gonna try and do. We'll want to interpolate between different values of table. So let's say we have a very simple table, 30, 45. No, let's draw it like this. Sorry. It starts at like -180 ... 30, 45. I say 35 and I draw 34. Yeah, let's do 35. ... Here's one column of the table, and here's the next one. I'm going to put theta, sine theta. And here's like sine of 30. Here is sine of 35. Now, this is good if we want the sine of 30, but let's say we want 32 degrees. How do we find sine of 32 degrees? Well, we don't have an entry in there, but we can kind of guess based on the values of 30 and 35. Here's what we want to do. We'll want to use linear interpolation, and just a quick review of that. Let's say here's 30 and here's 35. Sine of 30 and sine of 35. We know what these are. All of these quantities are known to us because they're in the table. What's not known to us is the value at 32 degrees. I'll write this as like degrees. What's this quantity right here? And we'll need to find that question mark. I'm going to draw a few triangles to kind of illustrate what's going on here. I know some of you may understand what's going on, but I want to make sure we have like a graphical conceptual understanding. Okay, here is 30, 35, and 32. What I want to do is I'll write this as like x low, x high, and this is, well, I'll just call this x. And we want to find what this quantity is. So we know what this distance is. We know what this distance is. We want to find this one. I'll put a question mark, and we know what this is. What all this boils down to is we'll need 4 quantities. We'll need this. No, let's use a different color. This, and this. Underline it here as well. Those 4 quantities will let us, so let's just find those first of all, and then I'll show you how we're going to use it to figure out what this question mark is. Okay. Now, I'm going to call this, let's do this, x. Yeah, let's use this terminology to be consistent. X low, x high, y low, and y high. So this is obviously going to use something in angle, right? Or angles on our x-axis. So we're going to want to use the table angles. Now the question is, how are we going to want to locate 30? You know, I have a bunch of dots before this. So how do we find the index of that? Does anyone have any ideas on how we locate this 30? If I gave you this tab underscore angle, and I wanted you to locate where this 30 was. So the condition we want to use is this. We're given 32. What is the highest angle that is less than 32? How do we code that? It gives a few seconds to think about this. What function do we need? What functions do we need? Or function, if just one. How do we, okay, let's start with this. How do we find, sorry, it was something about to say something.
Oh no, I was just like wondering, like, is it one of like those simple functions like find or something like that? I've never used it, that's why I saw it. I don't know.
Well, how do we find the maximum of some vector?
Max.
Max. Let's start from there. Now, we can't do max of tab ang because, well, we can't find the maximum of the angles because that's just going to be like 180 or something like that. Something down here. We need to restrict our search to just all angles that are less than our given x comma xp comma q.
Oh,
What this?
Oh,
go ahead.
Sorry. Oh, would you do like max and then like you have it where like you just sort out all the values, or like not sort out, but like you can like write it in certain notation so it only gives you the values that are less than 32?
Sure. And what's that notation going to be?
It's like, well, I guess if your thing is named A, you do A, and then you do like the parentheses, and then on the inside you have A less than 32 or something like that. I don't remember the exact way. I've done it before though. But yeah.
Less than, we'll do x p comma q. Yep, looks right to me. You could do find parentheses that, but that actually worsens performance according to MATLAB. So this is the ideal way to do it. So I'll read this out. The maximum value of the part of the table angles that satisfy the condition, the angle is less than xp comma q, aka the index of our x, which contains a bunch of angles, that, like, this is our 32 basically. All this is saying is this is our 32 degrees. Now I want to make one modification. This is going to give us two indices. Oh, no, two outputs, I mean. It's going to be x low, and it's going to give us the index. What is that angle that's less than our 32 degrees, and where is it? We'll use this index to locate x high. This next step is going to be a lot simpler now that we know our index, because this is at the same location as our x. No, sorry. Let me do it this way. I'll put this before. This is it's the same location as before. But this time it's not going to be table angles. It's going to be table values. So this is the same index. It's going to be the indexed, let's say the 45th entry of our table values. Now, here's my question to you. What's this next part? How do we find the 35? Do we need to repeat all of this again?
Shouldn't it just be the next index?
Next index. Say that in MATLAB language. It's going to involve index.
Index plus 1?
Index plus 1. Yeah. Same thing here. Instead of table angles, we're going to do table values. We have our 4 quantities. And before I forget, let me just do this. unused. Okay, we're gonna use that eventually. Okay, here comes the interpolation part. Let me, if I can clear all this in 3, 2, 1. We're gonna use similar triangles to kind of figure this out. So remember, we know these 2 points, known, and this is known. This is unknown. We want to find what this point is. So once again, this is a some point. I'll do like x low, y low, x high. I should just abbreviate this as usual. X high, y high. We want to find x, comma, question mark. Well, I'm going to assume that this is like a straight line between low and high. And I'm going to say this. We're going to use point slope form. First of all, let's kind of write the steps here. Find the slope. Well, we know using point slope form that if we like we just connect the lines between low and high. We'll say like y high minus y low over x high minus x low. That's our slope. That's just rise over run, because this over here, that's going to be the difference between our x high and our x low. And this over on top is going to be y high minus y low. Now that we have our slope, all we need to do is this. Let's look at our little puny little triangle over here. And we'll say, okay, I know what this one is. This is like x minus x low. And I'll put numbers to these so it's like less letters later. But for now, we don't know what this quantity is. But we know our slope. We know that our m is equal to rise over run, question mark over x minus x low, aka our question mark is equal to m times x minus x low. Putting all that together, if we want to find the y value here, all we need to do is say, okay, I know that it's going to be y low plus question mark. Remember, this over here is question mark. Okay, I should say this. This isn't question mark. This should be y low plus question mark. And that's going to be equal to this. Y low plus m times x minus x low. And m is just this thing we got over here. I'll drag that over here. And what all that does is that's going to find the sine of our angle at that interpolated point. Let me clear this in 3, 2, 1. So putting numbers to that, if we know 30, and we know 35 degrees, and we know 32 degrees, that's like saying this. Here's sine of 30, here's sine of 35. So sine of 32 is approximately sine of 30 plus sine of 35 minus sine of 30 over, not that, rise over run. So that's 35 minus 30, all that times 32 minus 30. If you want to think about it like this, you're taking this vertical distance and then you're like scaling it down by a fraction of like whatever like the ratio of 32 minus 30 over 35 minus 30 is. So that's enough for the conceptual stuff. But how do we put this all into, well, we want to find our slope, right? Let's do slope equals, what do people think I should do for this? How do we translate this into MATLAB? I'll write a fraction bar. What do people think? Use these 4 values that we got.
Maybe
mean-
like the, oh, no, you can go.
I was gonna say just like m equals y high minus y low over x high minus x low. And then you could do like, I don't know, yx equals y low times m times x minus x low.
Oh, let me catch up. X high and X low. Like that? All right, what next?
Is there like a, no, you could do like yx or just y or something equals y low plus m times x minus x low.
So Y, wait, the first one was Y high or Y low?
I think y low.
Y low plus, and we have our slope, right?
Yeah.
Times, what's this next bar gonna be?
X minus x low.
X minus X low. Oops. Now let's be careful here. This is going to be a matrix. So what do we need to do with this one?
Element by element multiplication.
Well, I'm not sure if we could, but let's do it the way we're doing it, because we're doing it, we're looping through it like this. So the purpose of this for loop is to kind of do it. We're already going like element by element. We're like using indexing. So
That's
this over
hard.
here, let's use P and Q. Do this. P comma Q. That's like the element that we're working with in this iteration of the for loop. I think, I'm wondering if we could do it like element wise if we didn't have these for loops over here, because it might complicate like the max part of it. The fact that we're applying the maximum to like a single index versus like an entire matrix, that might complicate things. Yeah, there might be a way to do that. You need to be clever about it. Okay, one more thing here. What should this be? What should this y be? Where are we storing this? Think a little bit bigger picture. Where are we storing this y?
Is it sign
In
table?
the table.
Sign table. Let's see, what size is sign table? Here's the thing, if we do sign table, then every iteration of this for loop, we're going to reassign the value. That's not what we want.
Would it just be the table?
Then what are we going to have as sign table?
Or is there a way to like append every iteration to the empty matrix?
I think the cleanest way to do that actually would be like P comma Q. We'll just say, because the way we're setting this up is we're basically doing this. Sign of X equals sign table. I know the way they name this is a little weird, right? Because sign table is like sign of X, not sign of table. So if this were up to me, I would have named it like sign of X, but that's how it is. So these will be the same size. Like it'll be like, here's like a P, Q, and then if you take the sign of that, yeah, you get my point. So that's going to be P comma Q. And there's probably ways of doing that. Like, I think like another way to, if you want to do like the concatenation way, we could do something like, let's see. I'm not sure that would be a clean way to. No, I think that's a little messier, because like if we already had like well, let's say we do we're doing this row by row. So yeah, like we're doing it like this. Like here's the first iteration of this. We're gonna create like one row of it. Then like we'll go to the next P. Like this is P equals 1. This is like Q equals like 1 dot 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 100. And then once we loop over that, we'll do the second row of that. I mean, because the first time we'd be concatenating like a single a single value to like an entire row. And I think that will be a little bit messy unless we like did the rows separately and then like piled them together after each one. I don't know. I think it would. Yeah, it would be a lot of indexing. You could do it. I think there's a way to do it, but no, I think this is easier. If you take fewer lines to do it this way. But if you can make that work though, then be my guest. Clearing in 3, 2, 1. Nope. There we go. And I think that's it. Sign table. Let's not take too much time. Let's see if we can wrap this up by 10. Okay. So quick disclaimer. I haven't fully like learned these like Lagrange polynomials before. A lot of this was like me reading through like the PDF and kind of trying to understand it. But I think if you just go by the PDF, like it offers kind of a pretty solid summary of everything. So here's the idea. I'll just kind of sketch it out very, very quickly. ... You have 3 points. Number of points equals 3. The order polynomial we'll need is 2, aka 3 minus 1, because a parabola passes through that. That's the lowest degree that you'll need. If number of points is 4, ... you'll need a cubic. So order 3. Number of points equals 4. So we'll make use of the number of data points, and we'll call that n. Coefficients, we're going to have as like an n plus 1 by n array. So we'll kind of do a thing where like we reserve these for like the basis polynomials, and then this is like our actual polynomial, actual and basis. And that'll make sense if you like actually look at the part 0 and what it kind of tells you to do. And this should be n, this should be 1. I'll write it like that. Here's matrix. And it's going to contain let's see. Where do I want to do this? Here's our Lagrange polynomial. And if you hear Lagrange polynomial, think this like parabola or this cubic over here. A0, A1x. Let's do like 4 points. So it's going to be order 3. That's this cubic over here. We're going to represent it like that. And the matrix is going to be this. We have 4 coefficients and like 4 points to work with. So we're going to pull this out, and I'm going to see. Okay. Let me erase. I'll erase this eventually, but I just want to use this spot for space purposes. Here's how we're going to write this in matrix notation: A0, A1, A2, A3. And over here, we're going to put 1x, x squared, x cubed. And we're going to repeat that down the matrix. X squared, x cubed, 1x, x squared, x cubed. And one more thing, we're going to want to put a subscript here. This is going to be the data point. 1, 2, 3, 4, etc. And all of this is we're going to say is going to be equal to the y1, y2, y3, and y4. Now, this is like our a, this is our x, and this is our b. So we can do sort of like an a/b to figure out what these coefficients are. Now, the way they ask you to do it, and I'm gonna wonder if there is a way. No, I was trying to move this out of the way, but okay. Okay, I'm gonna need to erase this, but like me like 5 seconds. Let's try and fill in this line over here. First of all, who can explain to me why we start at 2 here? Because what line 10 does is it creates like a bunch of ones, like 1, 1, 1, 1, etc. This is what matrix creates. And remember like that A we want this to be, right? This needs to be like x squared, x cubed. So why do we start at 2 instead of 1? Or would you like to kind of fill this out and then we'll kind of see what the reason? If I hear sounds, I'm just gonna do this line.
Well, we
So-
want the first column to be ones, so we just leave it alone.
Mhm.
That's how we start at 2.
That's right. So if we're going to start at 2, and we're going to swap these ones. I'll circle this column. 1, 1, 1, 1. We'll circle this, and we're going to replace it with x1, x2, x3, x4. So in MATLAB speak, we're going to do x data. That's all you have to do. But if we go to the third column, we're going to want x to the power of 2. So we'll need to do this. Okay, I'm going to make a deliberate mistake here. What's wrong with this? Well, 2 deliberate mistakes. What's wrong with this picture?
Well, it's not going to change for each column.
So what's it need to be?
I think n.
Well, we'll want to do this one over here.
Oh, then yeah, I.
I. Okay, what else is wrong with this picture? Can we multiply a vector by a vector? Like by itself?
Oh, it needs to be element wise, I think.
Element-wise, yes. That'll create a vector that's like, it's not really a dot product. It's like, it's element-wise. So if you do it using no dot, just regular exponential, you'll get an error. Like, oh, the matrix, the size doesn't match up. You can't multiply like a 4 by 1 by 4 by 1. You can multiply 1 by 4 by 1 by 1 by 4, but you'll need to like transpose it a little bit. Now, what are we going to do next? Yeah, this is solid. This is just assembling the coefficient. Like this is assembling that thing I kind of erased in this region of the woods with like 1 x squared, x to the power of 3. Excuse me. Okay, what are we doing in this neck of the woods? This is something they mentioned in the PDF. I'm not even sure it was in the textbook. Where you'll want to assemble this like y basis. And what this basically is this, you'll want a coefficient that's, let me just use the PDF as kind of like notation reference here, because I want to make sure that we match that up. This Lagrange, right? Okay, they're saying this. I'll get rid of this part. What I'm going to do next is I'm going to write like the kind of the notation for how we assemble these like bases. So here is like some Lagrange polynomial. Well, okay, the complete polynomial is going to look something like y p. What did they say? yi? Yeah, yi pi. I changes, like it's like this I over here. It goes from 1 to n. So it's like this number right here. This is I. 0, 1, 2, 3, all the way to like n minus 1. This is n minus 1. Well, I guess, okay, this is like a little bit different, but it's like the, no, I think it's actually like the number of the x data. It's the same like numbering, either 0 to -1 to n minus 1 or 1 to n. But let me just write this out. It's, okay, so P is going to be like a bunch, it's gonna be a vector, right? Yeah, it's going to be a vector of all zeros except for one number. So let's say my I equals 3. So the third element of that's going to be 1, and then that's going to be 0. That's what that looks like. Yeah, hold on. Let me just kind of stop sharing for a moment. And then we'll move over to the, what's it called? PDF reader. This is what I'm looking at right now. And this is how what we're going to do next in the skeleton code, well, / solution. This is what we want to assemble, right? Let me scroll a little bit up so we can see like the, oh no. Yeah, I can't fit this on the one page, but like this is the idea. We're going to want to assemble a coefficient, something called coefficient. And we're going to want to use these, like the basis polynomials, and then like this is the actual Lagrange polynomial. I'll explain this as much as I'm capable of, but like just again, I don't fully understand like the math that's going on here. But based on what they're telling us is this Lagrange, this final thing in this last row is going to be like the summation of like all of our like y times pi's. So here's going to be, I wonder if it's worth the time to kind of go through this. Okay, how about this? Well, go through the code, and then if we want, we can try figuring this out later. So kind of a result of me not fully understanding this part. But we'll go back to here, and we're going to want to assemble the top part of the coefficient matrix that I kind of talked about before. With like, I'm sorry, but like the annotations earlier got deleted, but like you can check the recording for that. Should be posted by noon. Here's this top part over here, this for loop. So we have a y basis, and that's going to be like the 0, 0, 1, 0 we kind of talked about. I'll write it as like 0, 0, 1, 0. This is the third iteration. And we'll say, well, we know what our matrix is. And we'll say this is sum A0, A1, A2, A3. These are known, this is not known. How do we find what this is, given the matrix and given a y basis?
Inverse of the matrix?
Sorry, say again?
Oh, the left column multiplied by the inverse of the matrix.
Inverse of the matrix. Left multiplied or right multiplied? So what I'm saying is like, is it to the power of -1?
Yeah, inverse times the vector.
Times y basis. This needs an underscore. Yeah. This, or we could do like matrix.
Can we just do a backslash type thing for these?
Yeah, that works too. Yeah, I'm not sure if this is like invertible or not. Oh well. Yeah, I think I prefer backslash just in case like this thing doesn't have a, no, to the power of -1, does that do a pseudo inverse? I forget. I know this works. If it's to the power of -1 requires it to be invertible, I would caution against that and maybe like have the backslash. I need to look that up to be completely frank, but Let's do this for now. Yours might work though, the inverse, to the power of -1. So that'll compute all this first half, and then I'm not sure what this is actually going to look like. It's going to depend on like what the x data is. So for this last part, I think like they tell you that you can. Yeah, how would you guys do this next part? So what did I say? Like this last part was going to turn out to be.
Coefficients of like the Lagrange polynomial thing, right?
Yeah, we're gonna sum up all of the like y px's. So I think the way they want us to the sum of this. Okay, I'm gonna do the way that like I think the PDF wants us to do it, and I'm gonna show you after that the way the solutions actually have it. So here's what the way that I'm interpreting the PDF wants you to do it. Sum of coefficients. Let's see, 1 colon. Let's see, what's the number? It's n, right? Yeah, we know we're n. 1 colon n comma 1 colon. No, let's just do colon. Look, I need to test something out really quick. Sum of magic 3. Okay, that works. Now seeing whether it's summed in like this way or like this way first. So that should work. Coefficient comma colon. And that should give us the final, like we're gonna sum up over all the rows of that, and that gives us the Lagrange. Yeah, not sure if that actually works, but the way they actually ask you to do it is this: matrix backslash. I think. Oh wait, one more thing we have to do actually. This gives us a column vector, and I'll need to do this with the final one as well. This needs to be a row, not a column. So that's just to avoid any dimensionality stuff. Matrix. So instead of y basis, we're just going to use y data for that. Y data. And let me just pull up the solutions to make sure that that's actually correct. I believe it is. No, not that one. My Lagrange. There we go. Yeah, there we go. They use transpose, but you can do that apostrophe. Kind of make sure of that. Okay, I did make a mistake actually. So it's not to the power of I. It's I minus 1.
Sorry.
I didn't catch that either. So there are actually 3 mistakes. Okay. I'm going to clear this annotation and then open up to questions. It's 10:07. I'll stop the recording because that we've went over everything. Wait, where's the? Oh, found it. Stopping the recording.